Hey folks, we're talking about mechanical energy and conservation today. This is the beginning of assignment 3.2. These videos are probably the most significant videos for this unit because they deal with our first conservation law, and that's a big deal in physics. So let's begin. We've introduced mechanical energy, and so we're really just going to talk about conservation today, what it means, and what it means for mechanical energy. So there's different versions of definition for conserved, and there's a very specific definition in science for what it means when something is conserved. I have 3 bullet points. We could probably keep going on this for a while, but I've boiled it down to like just 3. So if something is conserved in science, that means that the total value is constant. That implies that like things can be changing, but the total stays the same. This is the first one because the way that I like to write equations in this unit and all units where there's a conservation law, I base it around the idea that the total value is constant. But you will also see in some of like the College Board questions, this second one pop up. The total change in value is constant. Now, these two are different, but they wind up describing the same thing. I'm just going to show you some symbols for what that means. If the total value is constant, if A is conserved, that means that the initial value of A is equal to the final value of A. That's what I mean by the total value is constant. The next one is the total change in value is constant, and it's going to mean the same thing, but that in symbols would say delta A equals 0. So the total change in value is, sorry, that shouldn't say constant. The total change in value is 0. And so there are 2 different ways of saying the same thing. The last one is starting to get into even more specifics. It's more complicated. The change in value for a system is equal and opposite to the change in value for its surroundings. We kind of bend that a little bit in the world of energy because we don't talk really about system and surroundings so much, but we talk about types of energy or forms of energy. In the whole grand scheme of things, system and surroundings is probably the most common way to talk about how energy moves through things. So I'm going to use that definition. Now, what this means is if we kind of like expand this delta A, the change in value for a system and its surroundings. So let's see, if we say delta A for system 1 is our first symbol, if I add that to delta A for system 2, if those are the only 2 systems that are interacting, then they would have equal and opposite changes in value, which would bring us to a total change of 0. So things can change, but the overall total stays the same. So those are just some ways to think about what conservation means, and we will learn 3 conservation laws in this course. I believe there are 9 in total for physics. Energy is conserved. So we talk about like just a sliver of what energy is. And so if we just talk about energy on the whole, we can say something like the total energy in the universe is constant. And so that's like, in theory, like before the Big Bang, during the Big Bang, after the Big Bang, and every minute since, the total amount of energy available in the universe hasn't changed. And so what that means is that energy can be transferred or transformed, but not created or destroyed. And that's pretty general language for conservation, that you can move it from object to object. You can sometimes change the form of the energy, what type of energy it is, but you can't make new energy and you can't destroy energy that exists. And so that's like the universe as a whole. We're only talking about mechanical energy. So we can't always say that energy is constant. We can sometimes say that mechanical energy is constant. We have two criteria. We're going to learn a lot about the first one in this section, and then when we get to the end of this unit in the final section, we'll learn about the second one a lot more. And so for now, we'll just focus more on the first one. The system that we analyze, if mechanical energy is to be constant, the system must be closed. And to say a system is closed is to say the net force on the system is equal to 0. Objects that have a net force will accelerate, and there can be acceleration in a closed system, but that is just because the object that causes the other object to accelerate is part of the system. And so we will talk a lot about the presence of the Earth in a system, because Earth causes gravity and gravity causes acceleration. So that's where we're headed with that one. The second one is a little bit more nuanced. In order for mechanical energy to be constant, only forces associated with potential energy act on the system. To say that another way, mechanical energy is constant only if the forces that are acting are capable of storing energy, because that's the key to conservation of energy, is that energy is moved from between kinetic, motion energy, and stored energy, or vice versa. If both of those are true, then we can go back to the very top and we can say that the change in mechanical energy is 0. And the other way we can write that is that the initial amount of mechanical energy is equal to the final amount of mechanical energy. Now, those two statements are exactly the same thing, and I just want to show you how you get from one to the other. This is probably the most common way that a problem would have you think about this. The change in energy is equal to 0. Well, change in something is always the final value minus the initial value. And if that change is equal to 0, oops, should be a minus sign, then I can add initial energy to both sides, and I get this other statement on the right, that the initial energy is equal to the final energy. So I like to write things this way because it tells a story from start to finish, and I continue to do that throughout the unit, but the College Board also wants you to be able to think through this delta E equals 0, 1 for some conceptual stuff. That's it for the first one.